Now we're going to move from into Chapter 2, Section 2, and it's General Systems of Linear Equations. So Chapter 2, Section 2, and it's General Systems of Linear Equations. So the first thing we're going to do is going to define what we're going to really focus on, and that's called pivoting. And what you're really doing for pivoting is you're making the entry into a 1. Making the entry or creating or transforming. I probably should use the word transforming. Let's change it to transforming. So you're going to transform the entry into a 1. Second step is you're going to transform the other entries in the same column into zeros. And this is really what we did last section when we started using Gauss-Jordan elimination. But now, what the text is going to ask you to pivot around this number. All right, so here's our first example. So pivot about the circled element. Okay, so all you're doing is you're pivoting. It's not asking you to solve anything, right? We're not saying solve the system or solve the equations or anything like that. We are just saying pivot around the circuit, about the circle element. And we're going to pivot around this -6. So our goal first thing is to transform that entry, -6, into a 1. And how we do that is we use our elementary row operations. We are going to multiply that entire row by -1/6. So say -1/6 times row 1. So 18 times -1/6 gives us -3, and then -6 times -1/6 gives us 1, which is our goal there. And then 15 times -1/6 actually becomes a little larger of a number, but when we simplify it, it becomes -5/2. All right, because it's -15/6, and 3 goes into both 15 and 6, so we simplify it to be 5/2. And we still have 5, -2, and 4 down here. Now, so that's the first step. The second step now says transform the other entries in the same column to zeros. So what we're going to do is this -2 down here, we want that to be a 0. In order for that to happen, we multiply the top row, the first row, by +2, and then add that to the second row. So 2 times row 1 plus row 2. That will give us, remember, we're not changing the first row, so I'm just going to rewrite that. So 2 times -3 is -6, right? Because I'm doing 2 times -3, so that's -6. And then 5 plus -6 is -1. And then 2 times 2 times 1 is 2. So -2 plus 2 is 0, which is our goal. And then 2 times -5/2 is just -5. So I have -5 plus 4, which gives us -1. And we're done. We've done exactly what it's asked us to do. All right, so far what we've done so far is we've only achieved one answer for X or Y or Z and whatever we've been doing, but there are more than one option. So the types of solutions that you get or that you can achieve. All right, you can only get one of these. And the most common one that we see a lot is that we have one unique solution. And that's really our goal when we use systems. We try to say, if we have all of these different equations or situations with variables, we want them all to work at the same time beautifully. So how do we maximize this, or how do we minimize this, or how do we all get them to connect? And that's what we usually use these for. The other way is to say, hey, they don't connect. So if they don't connect, meaning, what does that mean? That means that we have no solution. And the last one is that they, oh goodness, they always connect and intersect. This is infinitely many solutions. All right, so these are the types of solutions we have. Now, with one unique solution, depending on how many equations I have, I could have, let's say, this represents my x, this can represent my y, and then this can represent my z. You can clearly see that right here, there is one unique solution right there. Okay, that would be a good representation of one unique solution. Now, if I was to go and find no solution, a no solution might look something like this. There is no solution to this because they do not all intersect in the exact same spot. Notice how this one has the point right here. This one intersects here, here, here. But not once do they all intersect each other. So therefore, it's no solution. Infinitely many solutions is basically, here's one, here's the next, and here's the next. They're all right on top of each other. So everywhere they intersect throughout the entire line that you're given. All right, let me see if I have room. I think I have enough room here. So example 2 now, right? I believe example 2. We're going to find the solutions. I'm going to give you a system. X minus y plus z equal to 3. X plus y minus z equal to 5. Negative 2x plus 4y minus 4z equal to 1. And what I'm going to have you do is, I'm actually going to have you pause this and come back to it. All right, I want you to be able to know that we're going to make this leading coefficient to be 1. And after we make that leading coefficient to be 1, then what we're going to do is, then we're going to pivot that. Right? So in fact, here, let me start you off. The first thing we need to do is write a matrix, right, as an array. There's our array. What we need to be doing is we need to pivot around that 1. In order to do that, first step is done. It is a 1. The next step says everything else in that column has to be a 0. So we need to make this become a 0 and this become a 0 by using elementary row operations. Right? Once you do that, then you're going to pivot around this value. And then make this become a 0 and that become a 0. All right, and then see what happens and come back. So go ahead and pause now and try it out. Run into a problem? And you might say, yeah, because I had nothing at the bottom of my Z column to solve for. And you're right. You run into this problem right here. Let me highlight it here. Well, that wasn't a highlighter. You run into this. Well, if I had to write this as an equation, this says 0 equals 5. Can 0 ever equal 5? So the question you ask yourself is, can 0 equal 5? I'll answer that easy. No, never. So the answer to this system is no solution. So there is no solution here. which means that there is not a value for x or a y or a z where they all intersect. Now I'll show you something else. What happens if we get to the end and it's 0 equals 0 at the bottom? What does that mean? That means you have something called infinitely many solutions. So if you have 0 equals 0, then you have infinitely many solutions. I'm going to show you a problem where you have infinitely many solutions. All right, so example 3. Find the solutions. X plus 2y minus z plus 3w equal to 5. And then I have y plus 2z plus w equal to 7. All right, so if I'm looking at this, and I have to write my matrix first. Matrix first says 1, 2, -1, 3, and 5, 0, 1, 2, 1, and 7. Well, when you try to look at the first value here, it's already a 1, it's already a 0, so we've already pivoted around this, so we're good. Next we come here, so we're going to pivot around this 1, which means the above value needs to be a 0, so let's do that operation. So that one's simple. We're going to say -2 times row 2 plus row 1. So the second row doesn't change. And we have 0 times -2 is 0 plus 1 just becomes 1. And then here we have -2. -2 times 2 is -2. So we have -2 plus 2 is 0. Then we have -2 times -1. I'm sorry, -2 times +2, which gives us -4. So -4 minus 1 gives us -5. Then we have -2 times 1, which is -2, and -2 plus 3 is just 1. And then lastly, we have -2 times 7, which is -14, and -14 plus 5 is -9. So this isn't necessarily at the end says 0 equals 0, but look what we have. We have so many different solutions to this because it varies based off some variables. Because if I rewrote this as a system, it looks like this. Remember, this is our X column, Y, Z, and our W column. So when we rewrite this, it looks like X minus 5Z, and actually I'm gonna, I'll write like that, I'll give a space, plus W equal to -9, and then I have Y plus 2Z plus W equal to 7. This is my system. So I'm trying to say, what does X equal, what does Y equal? Well, we could find what X and Y equal, but they're just gonna give us more values, more variables, not values, just say variables. So X equals, how do I find what X equals? Well, I can just simply solve this for X. So I would move this to that side and move this to that side. So I would have to add 5Z to both sides and subtract W from both sides. So X equals 5Z minus W minus 9. And I can tell you what Y is, but in order to do that, I have to move all this over by using the inverse operation. So Y equal to -2Z minus W plus 7. So great, X and Y are some values, but what about Z and W? What's the restrictions there? Well, guess what? There aren't any. They can be any value they choose. They are free to roam. And then once we get a Z and a W value, Then we can find what x and y are. So for instance, let's say that z is 1 and w is 2. Again, I made these up. All right, we've made these up. These are not specific. They didn't say, oh, hey, how'd you know z was 1 and w was 2? You have no idea. Just throwing it out there. So if that's the case, then we know, hey, we know z is 1, w is 2. Those are the easy ones, right? We took care of these. Now we have to take care of what x and y are. So x is 5 times z, which is 1, minus w, which is 2, and then minus 9. So when you put this in your calculator, you do this in your head, it's 5 minus 2 minus 9 gives you negative 6. So in this case, x is negative 6. Next case, I have y. And y is negative 2 times z, which is 1, minus w, which is 2, and then plus 7. And this math gives you 3. So the answer to this is z is 1, w is 2, x is negative 6, and y is 3. This would be your solution. But now these vary and depend on what z and w are. Therefore, you have a whole bunch of different types of solutions you can have.